Okay. Last class we finished up with the 6.3 notes. Today we are moving on to the 6.4 and 6.5 notes. After that, the sub will provide you with the 6.1 to 6.5 quiz review. Please hang on to that before we take the quiz on Monday. We will go over that together, talk about any questions that you have before we move on to the brief quiz. After you finish the quiz review, if you finish it today, work on worksheets 39 and 40 or the MyOpen Math assignments for 6.4 and 6.5. .4, today's lesson is on the base multiplier property. Little algebra just to talk about, but the power 7 to the third, or 7 cubed, means 7 times 7 times 7, which is 343. If you raised it one more time and went 7 to the fourth, it would be 7 times 7 times 7 times 7, or 7 to the third power times 7, which is 2,401. Just a quick example there. The property that we're going to look at says, for an exponential function of the form f of x is equal to a times b to the x power, if the value of the explanatory variable is increased by 1, remember, explanatory variable is represented by x, so if that's increased by 1, the value of the response variable is just multiplied by b. We'll see how that's worked out. So example 1, let's say the given function describes the relationship between the price of a product and the number of months that the product has been on the market. Your explanatory variable is the number of months that it's been on the market, right? That's time, that's our x. The response variable is the price of the product. We're given the function p of x is equal to 100 plus 2x. Our starting value is, 100. And each month that the product has been on the market, x, the price increases by 2. Right? So the price of product product A, increases $2 every month. What type of function is described? I want you to think about it right now. This describes a linear function because there is a constant rate of change. That constant rate of change is 2. You're increasing by 2 every single time. In the context of this problem, right, and I kind of mentioned it already, the starting price is 100. The starting price is 100. That's what that constant value means, the constant term. And in the context of this problem, the coefficient of 2 means that the price increases by $2 every single month. That's our rate of change. But this is a linear example. Let's say that the function describes the relation between price of product B and the number of months that it's been on the market. Here's your function. P of x is equal to 5 times 2 to the x power. What happens to y as we increase x by 1? It's being multiplied by the b value every single time. As x increases, say x starts at 1, then it's 5 times 2 to the 1 power. If it increases by 1, it's 5 times 2 squared to the second power. 5 times 2 to the third power, cubed, right? So on and so forth. But we are just multiplying that by 2 every single time. We're adding another into our explanatory variable, another number into our exponent. When x is 0, what is p? And I want you to think about what it is right now. We don't need to do any substitution. We can figure out just by looking at this. 5. It's our a value. Our starting value is our a value. Where do we start? A, 5. And the pattern, right, think about your multiplier, what are we going to increase by every single time? We're going to increase by a multiple of 2. We're going to multiply by 2 every single time. So the 5 represents the starting value, being $5, right? The starting value of that price. And the 2 means that how much the 2 is a multiplier. It's how much the price is increasing every single month. The price increases by $2 every single month. Now we're going to use the information we're going to use the information from that equation to answer the following. What happens to the output value if the input value is increased from 2 to 3? Well, x was only increased by 1, right? Instead of x being 2, x was 3. Instead of x being 2, x was 3. So y is just multiplied by 5. That's the only change. That is our base multiplier property. As we increase x by 1 from 2 to 3, we are just going to change by the multiplier, which is 5. But now let's see what happens when we change by 2. X increases by 2. So in order to get from 2 to 3, we had to multiply by 5. In order to get from 3 to 4, you have to multiply by 5. So you're increasing by a multiple of 5 to get from 2 to 3, and then doing the same to get from 3 to 4. So y is being multiplied by 5 times 5, which is 25. So if you're increasing by more, you're not necessarily going to just be increasing by the multiplier, but in this case, it's increasing by the multiplier from 2 to 3, then increasing by the multiplier from 3 to 4. 5 times 5, 25. Let's see it work through in the next one. What happens to the output value if the input value is increased from 20 to 21? And with this function, f of x is equal to a times 10 to the x. And we don't even need to know what the a value is, right? We don't care about the starting value. All we care about is the multiplier right now. Well, x only increased by 1, so y is multiplied by 10. So we just use one of our multipliers. Example 4, what happens to the output value if the input value is increased from 30 to 32? Well, our input, our x, increased by 2. So to get from 30 to 31, our y is multiplied by 5. From 31 to 32, or sorry, not 5, 10. Right, different example. In order to get from 30 to 31, we have to multiply by 10. In order to get from 31 to 32, we again need to multiply by 10. So y is being multiplied by 10 times 10, which is 100. That was 6.4. 6.4 was pretty quick, right? Just talking about that base multiplier. It's just continuing the pattern, right? How could we continue the pattern, right? Maybe we're at part of the table where it's 10 and 20 and 30, right? And we're increasing by 10 every single time, 10 inputs every single time. Well, then we have to increase our multiplier 10 times. 6.5, talking about graphs of exponential models. As we know, and we talked about last class, we can either have growth or we can have decay. And every single time your horizontal asymptote that we're going to see is 0. Right? We're never going to cross that. We're either growing or we're decaying. And we talked about if the base of the function, or the multiplier, is greater than 1, you're going to see growth. But if it's in between 0 and 1, that's where you're going to see decay. And that's where we saw our fractions, where we had maybe 2 times 1/3 to the x power. That's decay. But 2 times 3 to the x power, that's growth. Looking at our graphs, and our tables, we wouldn't even really need the functions, right? We know, and let's just look at this example first. We know what our starting value is just by looking. When x is 0, what's y? 3. So a is 3. It's our starting value. And looking at our graph, that's our y-intercept is 0, 3. So 3 is our starting value, a. What are we multiplying by every single time? 2. Our a is positive. Our b is greater than 1, which means that our graph is increasing. That's growth. Our graph is increasing. Now let's see how this changes when we have a problem where we're looking at decay. Well, our starting value is 0, 4, right? It's positive. It's a y-intercept. And what we're multiplying by every single time is 1/2. 4 times 1/2 is 2. 2 times 1/2 is 1. 1 times 1/2 is 1/2. 1/2 times 1/2 is 1/4. So again, your A is positive, but your B is less than 1, and it's between 0 and 1. So we are decreasing. That represents decay. Increasing represents growth. Decreasing represents decay. And we can either look at that when given the graph, or we can look at that when we're given the table. As x increases, what happens to our y? Oh, well, it increases, which means we're going to have growth. As x increases, what happens to our y? It decreases, which means we're going to have decay. There's just the formal definitions there, right? And we did talk about that last class. If b is greater than 1, it's growing exponentially. Sorry, that was terrible. Growing exponentially. But if b is between 0 and 1, then we are decaying exponentially. Use that graph of the exponential function to answer the following. We need to make an input and output table, right? Just completing this table. Well, just based on the information that I know, right? I know my y-intercept, and I know one of the other points. So for my x, I'm just going to go 0, 1, 2, 3, 4. Make it easy on myself. I know that my starting value is 3, because that's when x is equal to 0. So my a is 3. And let's see. I mean, from 3 to 6, it looks like I multiply that by 2. And then I multiply by 2, multiply by 2, multiply by 2. So my multiplier, my b value, is 2. Writing an equation, we need this in function notation. So instead of using y's, we're going to use f of x. F of x is equal to a times b to the x power, where a is 3 and b is 2. 3 times 2 to the x power. And what we need to be able to do, either using the graph, using the equation, or using a table, is to evaluate it. So f of 1, remember this is just f of x. So this is saying when x is 1, what is y? When x is 1, what is y? 6. When x is 2, what is y? 12. And the reason why we filled out this table was so we didn't have to do it later when we were trying to do this. Now, let's talk about these. And again, f of x is equal to y. When y is 3, what is x? When y is 3, or when f of x is 3, what is x? 0. When y is 12, f of x is what? Or sorry, when f of x is 12, x is what? 2. Right now we're just kind of going in reverse. I give you the output, you're looking for the input. Use the graph of that exponential function, g, to answer the following. Here's your graph. I want you to try and complete the table. Go ahead, take a second right now. Just looking ahead real quick. All right. Completing what we know, right, we're going to make it easy on ourselves, go 1 through 3, or sorry, 0 through 3. I know 0, 2, I know 1, 8. 0, 2, 1, 8, looks like I'm multiplying by 4, so I continue that pattern. My starting value is A, 0, 2, 2. My multiplier is 4. Writing this as an equation, g of x, right, just because that's our function here, g of x, is equal to a times b to the x, where a is 2, b is 4. We evaluate the following. When x is 0, what is y? 2. When x is 2, what is y? 32. When g of x is equal to 8, what is x? 1. When g of x is equal to 128, what is x? 3. When we are graphing an exponential function, you need to identify 3 points in order to make a smooth curve. One of those points is when you're increasing your outputs. One of them is when you're decreasing your outputs. When we are increasing, we're going to multiply by the multiplier, b. When we are decreasing, we are going to divide by the multiplier, b. In one direction, you're going to be multiplying. In the other direction, you're going to be dividing. Let's see what this looks like. My my starting value, 0, 4. So I know my a is 4. In one direction, I need to go a times b. b is 2. So a times b. In one direction, I need to go a divided by b. My a is 4. I need to multiply by 2. I need to divide by 2. Then I can graph these 3 points in order to make a smooth exponential curve. And with the next example, it's a bit trickier because your b is less than 1, and it is a fraction. But I know my starting value is 4. I need to multiply by the multiplier, multiply by 1/2. What's the same thing as multiplying by 1/2? Dividing by 2. That gets me 2. Right, so regardless of whether you can do 4 times 1/2, you're going to get 2. Half of 4 is 2. Or you could just do 4 divided by 2. So now even though we're increasing our x, we are using division because our multiplier is less than 1. Going the other way, 4 divided by 1/2 is the same thing as saying 4 times 2, so 8. And we know that since b is less than 1, it's going to represent decay, going off into the right, decreasing. Okay. That concludes 6.4 and 6.5. Right now, please complete the 6.1 to 6.5 quiz review.